In this video, we're going to talk about Bode plots, and from the last video, we looked at pole zero plots, and we said that Bode plots are going to be a little bit more useful in really seeing the frequency response for circuits. Now recall, for the frequency response, we're going to set S equal to J omega, so we're going to get rid of that sigma term. And there's a few parameters that we care about, and they are the voltage gain, the current gain, the transfer impedance, and the transfer admittance, where the subscripts O and I just represent the output and the input. Now, oftentimes the voltage gain, current gain, transfer impedance, or transfer admittance is just represented by H as a function of J omega, or sometimes S. That's a little bit inconvenient, but that seems to be the way that textbooks prefer to do it. But just for clarity, we're going to define the subscripts V, I, Z, and Y. And that's going to represent the voltage gain, current gain, transfer impedance, or transfer admittance. Now we know that we can represent H as a phasor, where we have some amplitude, just the over bar over H, and then some phase angle, which we represent as phi or phi. And those two forms are interchangeable. But we want to consider a simple RC circuit where we know that the output voltage divided by the input voltage, or HV, is simply going to be equal to 1 divided by 1 plus J omega R times C. And we can represent that in terms of a magnitude and a phase angle. This term here on the left, and then the phase angle on the right. And we know from the pole zero plots that we're going to have a pole at omega equals J divided by RC. We're going to make a substitution for what we're going to call this natural frequency, omega naught, and that's simply going to be equal to 1 divided by RC. Now we can plug this omega naught into what we got for H subscript V, and what we can do is plot the amplitude, or magnitude in this case, and then the phase independently of each other, but with respect to omega. So we can see in both cases for the magnitude and that phase term, we get this decaying nature that occurs as omega divided by omega naught increases. Now we're not so concerned with the phase per se. There are applications where we are, but what we are going to primarily care about is this magnitude. And from this HV function, or this transfer function, we're going to define something as the cutoff frequency, and that's going to be when the magnitude is equal to 1 divided by the square root of 2. And we can see that this happens in this case when omega equals omega naught, so that's where we define our cutoff frequency. Now if when omega equals omega naught, we have a cutoff frequency, we simply say that omega, which is equal to 2 pi f, is equal to 1 divided by RC, or that the cutoff frequency is 1 divided by 2 pi times RC. So you can see that the cutoff frequency changes depending on what R is, or depending on what C is. And again, we simply define the cutoff frequency FC at the point at which the power is reduced to half its original value. So in this case, if we scroll back up, we can see that we had a cutoff frequency and the amplitude was equal to 1 divided by the square root of 2. But recall that HV here was equal to the output voltage divided by the input voltage, so we don't really have a power calculation there. So just to avoid confusion, that's why we got this 1 divided by the square root of 2 term here. But if we went through and actually calculated the power at this cutoff frequency, we would have half of the original power. Now this is what will bridge us into Bode plots. And what Bode plots do is they give an approximation of the frequency response of some circuit. The way that we are going to use them, it's not going to be 100% exact or precise, but it's good enough to get the job done, and it's a lot easier to interpret than the pole zero plots where we had this complex three-dimensional blanket that had poles and zeros and infinities and all that confusing stuff to work with. But to understand Bode plots, we have to familiarize ourselves with the decibel scale. We're going to say that H dB is simply equal to 20 times log base 10 times the magnitude of h. And to look at a quick example, we're first going to consider h as a function of s, and just recall that s is equal to j omega. We're going to say that h is equal to 1 plus s divided by a, which is also equal to 1 plus j omega divided by a. Now, if we convert h to the decimal equivalent of h, we get this 20 times log base 10 times the magnitude above, which is equal to the square root 1 plus omega divided by a squared. And this seems like a function that's pretty hard to figure out what's going on, but we're going to use some approximations. And first, we're going to look at the case where omega is much, much less than a, so that this term in the square root is approximately 0. So then h dB is approximately equal to 20 times log base 10 to 1, which is equal to 0. And we can throw on the dB just for clarity. Now, for the case where omega is much, much greater than a, now inside the square root, that omega divided by a is going to be the dominating term. And if we start to plot values for this, what we get is that if the ratio of omega divided by a is equal to 1, we get a 0. If that ratio is 10, our output is 20. If that ratio is 100, our output is 40. So what we can say from this is that we get a plus 20 dB per decade increase. So we know the behavior for omega much, much greater than a. Now we can actually start to look at the plot where you can see here for omega less than a, we get 0 dB, and for omega greater than a, we get this plus 20 dB per decade. And notice on this graph that the horizontal axis is log. So this is a fine approximation, but we have to consider that h is not equal to 20 log 10, or it's not equal to 20 log 10 times omega divided by a. But we can say we know the behavior for omega much, much less than a, and omega much, much greater than a. So our original function is 20 log 10, and then we have that square root term. And we can start to plug in what's going on at omega equal to a. What we get is 20 log 10 of the square root of 2. And that's going to be approximately equal to 3 dB. And then at omega equals half of a, h dB is approximately 1. So if we look at our comparisons, on the left here, kind of had this sharp inflection point at a, but on the right here, we can actually see the nature of what's going on for omega equal to a, or around that ballpark of being equal to a. So on the left here, we have a very rough approximation. On the right, we have a better approximation. Now in general, there's two rules that we really want to pay attention to. First one is finding the behavior as omega tends toward infinity and as omega tends toward 0. Sometimes we can't actually get to that case where omega equals 0 without the Bode plot blowing up, so we just take that limit. And then the next step is to dial in the critical points, like we did for omega equals a, just to find small details. And this was a fairly easy example. In the next video, we're going to look at some more complex transfer functions of h to really see what these Bode plots look like when they start to get complex.